Okay, here we go. We're looking at part 2 of our Unit 1 for limits. We left off talking about, taking limits analytically and what happens if we can't just plug stuff in. We're going to expand upon this a teeny bit more today and get back to a couple of these indeterminate forms and learn a few other things. First is the squeeze theorem. Notice if I were trying to do this analytically, what I'd get is 0 times sine of 1 over 0. And that 1 over 0 is no good. This is undefined. So what we need to do, I can't just plug this into a calculator. It's going to spit out an error. So what I need to do is come up with a different way to solve it. What I do know is that sine is always going to stay between two values. That's really annoying. Sine is always going to stay between two values. I know that in general, sine of anything is going to stay in between 1 and negative 1. If I think of the graph of sine, it looks something like this, where this is negative 1, that's 1. So I know this to be true. Now, what I have here doesn't exactly look like what I have here. But if I can make this inside this inequality look like that, we can maybe get some new information about what this limit's going to look like. So what I'm first going to do is manipulate this inside and make it look like this. Now, changing the inside or the input to a sine function has nothing to do with the outputs. I could put this as 1 over x. I could put it as 1,000,000,000 times x. It's not going to change the output. It's just going to change how skinny or fat it is. So it's either going to, go real skinny or really long waves. The next thing I have to deal with is getting this x in here, because I have an x over here. I have no x here. What I can do is I can multiply everything by x. So I'm going to have negative x. I'm going to have x sine 1 over x. And I'm going to have x out there. Now, if the limit of this and the limit of this adds up, I know, are the same thing. I know that has to equal this one in the middle, because it's like saying this. If I say 7 is less than or equal to x, which is less than or equal to 7, I know that x has to be 7. It's got to be a number bigger than or equal to 7 and less than or equal to 7. So it's just got to be 7. So we're going to look at what happens when I do some limits now. Let's note that we're taking the limit as x approaches 0 over here. So I'm going to take the limit of all three parts. I'm going to go limit x approaches 0 of negative x. I'm also going to take the limit of the inside. You're going to notice that the inside limit is going to be just that. We're not going to go in this circular path and try to plug stuff in here. I just know that the limit's going to equal some value, and we're going to analyze that using the outsides. 0 of x. So let's notice what happens with this on the left. I know that limit is 0, because I just plug in 0 into here. And I know that this limit over here is 0, because I just plug in 0 over here. So what I can say is that the limit as x approaches 0 of x sine 1 over x is bigger than or equal to 0 and smaller than or equal to 0, meaning that by the squeeze theorem, squeeze theorem, I could say that our limit x approaches 0 of x sine of 1 over x equals 0. And we're done. So these problems are all done very similar. Typically what you're going to see is you're going to see some sort of trig function, and then the inside is going to screw up at some point. Like if I plug in this 0, it screwed this up. That is typically what you're going to see in a squeeze theorem problem. There are a few other types that we might look at. 9 times out of 10, if not 99 times out of 100, you're going to see it somewhat formatted like this. So if you see tangent and it's 7x I don't know, 7x over x squared, something like that, you're going to have the same thing. So we're going to do some more practice with this. I just wanted to show one example. But let's go ahead and look at some discontinuities and talk about continuity in general. So we have some different discontinuities, and continuity in itself makes you think of continuous. So is something continuous? Is something not continuous? We have a few different types of discontinuities. We have this jump discontinuity here. You can see that my whole entire function jumps up and continues on. I have what's called a removable discontinuity. It looks like what happens is I have this, this function, this line, and I just picked up one point and I moved it up there. So removable and infinite. And we can see that infinite, at some point, it tends toward infinity. Or it could look like going up and down, kind of like this. You're going to notice that with each one of these, a good general rule is to draw the function, you're going to have to pick up your pencil. So like if I'm looking at this jump, I would have to pick up my pencil to go from here to here and then go back down. So that's going to mean it's discontinuous. Now the technical definition is as follows, and I want you to stay with me. I'm going to write a somewhat more friendly version of this. So, definition of continuity, and this is like confirming it, so saying yes. A function is continuous at a point. So, for example, A, B, A. So, the definition, I just use A. If this double F, some of you guys have seen this if you had me with geometry, other if you guys have not. This just means if and only if. Mathematicians and your teacher are lazy and they don't want to write all these words out, so they just came up with this if, double F. So if your point exists, so it's imperative that the point exists. If it didn't exist, it could be a hole. And all this mumbo jumbo. Let's look at it. So let's look at what the first part is. Limit as x approaches a from the left of your function is equal to limit as x approaches a from the right side, which is equal to that outcome of the function. Basically what this means is the point exists left and right limit match and they are equal. So we got to check a few things. We got to check the left-sided limit, we got to check the right-sided limit, and we got to make sure that the point itself exists. We're going to look at this with this type of question. This is probably going to be something that's a teeny bit up from the very basic case because we got this weird k going on. We're going to talk about that. So find a value of k such that f of x is continuous. So this is a piecewise function. You know that when, for example, x isn't 1, it's got some sort of parabolic shape. When x is 1, we got this going on. So we need to find a k such that it works out. So first thing I want to do is I want to check the left-hand limit and the right-hand limit, because essentially what I need to find is what this whole value here needs to be. So let's just walk through this. So I'm going to take the limit as x approaches 1, because this is where we have our discontinuity. 1 from the right of x squared plus 1. Now, I know, and I hope you guys do too, that this function looks somewhat like this. It is continuous, so the limit is going to match up. But what is it going to equal? It's going to equal, oops, not 3, it's going to equal 2. So we're kind of looking at this point here. Now, I also know that our limit as x approaches 1 from the left of the same thing is going to be 2 as well. From the left, I go to 2. From the right, I go to 2. So now I know I have this portion of the answer and this portion of the answer. Now, when I plug in 1, f of a, you can imagine that a is that 1. I need to get 2. So I know that f of a equals 2. Or I should say f of 1 should equal 2. Or f of 1 can also be written as k minus 4. If I were to plug in 1 with this piecewise, I get k minus 4 is what I have to use. So I know now that k is equal to 6. So what I want to do is I found my k value, and I want to show that my answer is correct with the definition of continuity. So I'm just going to essentially write some sort of statement, some sort of sentence, kind of wrapping all of our findings together. So I'm going to say the k, or excuse me, let's just say k equals 6. Let's say k equals 6. Yeah, let's go with because. No, let's go 1. K equals 6. When applying the definition of continuity, where k equals 6, we get the limit as x approaches 1 on the left equals the limit as x approaches 1 on the right, which is equal to f of 1, which is equal to 2. The AP doesn't require this 2. I like it, because basically I can go back into your work and say, okay, am I finding this 2, what all these 3 things are equal to? Am I finding that in your work? Okay, I found one of them here, and the last one's over here. Good, I know that you know what you're doing. So the definition of continuity is really important. We're going to be working with this a lot. This whole idea that the left side equals the right side, and it equals the point, and the point exists. That's important. So let's go on and look at some infinite limits. So this is basically what happens when I go and plug in infinity. This is essentially end behavior. And we're going to describe it in a calculus sense using limits. I know last year we kind of just, or if you're in AP pre-calc, I should say, we kind of described end behavior as like this ends up, starts down, that sort of thing. And then we kind of started to put some names to it. And we touched on limits a little bit, but this is where we're really going to get into it. Essentially, we're doing, why is this plus and minus infinity? Let's just go positive infinity. Essentially, we're going to do the same thing. We're just going to plug in infinity and see what happens. Yeah, let's just plug infinity and see what happens. Well, we're going to get, obviously, infinity over infinity. It's kind of like this. But the main gist of it is that infinity to the 5th power is so much bigger, like this 10 doesn't matter. So what we're actually going to do is find a way to simplify this down. And what we can do is we can take the highest degree in the numerator and denominator, and we can divide them out, and we can see what the end behavior is going to look like. So I can almost ignore this 10. Really, all I'm going to do is look at these 2 ideas. And if I have x to the 5th over x to the 3rd, I know if I simplify that, I'm going to get x squared. Now what I can do is take that infinity and plug it in. So I will get infinity. Now, another way to do this is with the following. So let's say I have this sort of setup. I'm going to take the highest power, and I'm going to divide everything by the highest power. So I'm going to go x to the 5th plus 10 over x cubed, and what I'm going to do is I'm going to divide here. Oh, not by x to the 3rd, x to the 5th. and x to the 5th. So let's see a few things that happen. This is going to equal 1. So I'm going to have 1 plus 10 over x to the 5th when I'm talking about plugging in infinity. So it's really 10 over infinity to the 5th. We're going to see what that looks like in a second, but we could probably guess that that's going to be a really small number. And then on the bottom, we simplify down to 1 over x squared. And as we keep on going, if I rewrite this x squared as infinity squared, because we're really plugging that in, we're going to see that I have 1. This is kind of like 0. And this number here is also so small that it's kind of like 0. If I have any number over something with infinity that's so small, or an infinitesimally small number, it's going to equal infinity. So this is equal to infinity. Now, obviously, if you type this into a calculator, it's not going to come out like that. You're going to get some undefined. Basically, what I'm saying is this here is still a number. It is so infinitesimally small that when I put 1 over it, a really small number, it gets stupidly big. It's kind of like this. So if I have 1 over 1, that's greater than 1 over, how do I want to write this? Let's go, or let's think about the other way. If 1 over 1 is greater than 1 over 2, or 1 over 10, which is greater than 1 over 100. And if I keep going down, you get 1 over infinity, and that's such a small number that it really doesn't even matter. The same way goes for this. So we're going to get a lot more experience with these types of problems, plugging stuff in. This is the really simple way to do it, just by deleting off these other terms that don't matter and simplifying. So let's look at something like this. This is where that number over infinity is going to come into play. We talked about the fact that sine lives between two numbers, -1 and 1. Cosine does the same exact thing. It lives in between -1 and 1. So I know that on top, this isn't like a technical super math thing, that our output, I'm going to call it y, is always between -1 and 1. Even if I put an infinity into here, it just sits there. It's in between -1 and 1. Now, on the bottom, I still get infinity. So I have a number over infinity. That's going to equal 0. That's going to equal 0. Infinity is so much larger than any number you could think of that it's just going to equal 0. Even a million, even a billion, so on and so forth. It's always going to equal 0. Now we get into some fun stuff. If you guys don't remember what a factorial is, if I have 6 factorial, that equals 6 times 5 times 4 times 3 times 2 times 1. So if I have x factorial and that x is infinity, this is like infinity times infinity minus 1 times infinity minus 2, infinitely many times. So we could guess, using our greater reasoning, that which one's going to be bigger, infinity factorial or infinity to the 5th power. And you would be right in saying that the top is going to be bigger. And if the top is bigger, and it's such an infinitesimally larger number, this is just going to equal infinity. So these sort of relationships are going to be important, and we have this real quick, I don't want to say cheat sheet, but little, I don't know, thing to reference. So anything where it's like infinity to the infinity power is going to be the largest. Then the factorial. If I have a number to infinity, so this is basically saying like 2 to the infinity is greater than infinity squared, which is then bigger than natural log of infinity. So that's basically what that is saying. This is going to be important to write down. For questions like this, it makes it really easy. You just find whatever the largest is. And if it's on the top, if it's infinity. If it's on the bottom, it's 0. Now we're getting to the fun stuff, the intermediate value theorem. Here we go. Basically what this does is it ensures and proves that points exists on continuous functions. Let's read. So if f, a function, is continuous over a closed interval from a to b, and d is between f of a and f of b. So it's important to note that d is a y value, f of a is a y value, f of b is a y value. So like f of b is, this is f of b, and this is f of a. We could obviously see that d is between these two values, so that's kind of what we're looking for there. So, and what did I say? And d is between those two values, so that's kind of just a different way to write it. It doesn't matter if the second one is first or higher or lower, it doesn't matter. So a could be first, b second, or b then a. It doesn't matter. Then the intermediate value theorem guarantees that there's at least one number c, so this is an x value, s/t, that means such that our function at that point equals d. So this kind of, doesn't make that much sense as to like why we're doing this. Let me put up a different example of something that's not continuous. So let's say I have a function, or I have an endpoint here of a and an endpoint here of b, and let's create a function that's not continuous. Let's say we go up here, we got a point, and then we start down here. And let's say, without the intermediate value theorem, I wanted to say that some y value at this point d exists. So that would be somewhere here. We could obviously see that my function that I drew up doesn't hit there. What the intermediate value theorem does is that if I have a continuous function, it shows that this value d will exist. So it shows that this will exist. Now, it's easier to just go ahead and do a problem than just sit here and talk about it all day. So let's go ahead and take a look. So we're going to let our function be sine of x. I want to prove that for some value over the interval from 0 to pi over 2, that there must be some value d, which equals 1/4, where f of x equals d. So let's think of a few things that are important in this intermediate value theorem. The first thing is that it's continuous. I know that sine is continuous. So our continuity idea is done. So we are continuous. What I need to check now is that my y values match up. So these are x values here. If I draw up this function, it kind of looks something like this, where this is pi over 2, we got 0. And I want to see essentially if 1/4 exists up on there. I want to see where that exists. So I know it's continuous, and now we're going to deal with the kind of bounds. So f of 0, I want to check if that's in between, or excuse me, if 1/4 is between f of 0 and f of pi over 2. So this means I'm going to take sine of 0 and compare it like this. And, oops, not f, we're going to go sine pi over 2. Now I know sine of pi over 2 is what? It's 1. Thinking about the unit circle. And sine of 0 is 0. So this part also checks out. So I have the two requirements to say that that point D is good, that 1/4 is good, and there's going to be an x value such that f of x equals 1/4. So I have all the tools I needed. Now what I need to do is craft a statement going ahead and prove this. And it's going to look something like this. So the first thing I need to do is mention continuity. If I don't mention continuity, my answer is not going to be correct. So what I'm going to say is note f of x is continuous. We don't have to prove this. We just have to make note of it. If I was given a piecewise function, something like we did earlier with this, I would have to prove that this is continuous first, but that isn't the case here. So I'm going to note that f of x is continuous, and I could leave it at that. Well, I'm also going to mention it's continuous over the interval. So, thus, being continuous over 0 to pi over 2. Now, I want to mention something about these y values. Also note that f of 0 is less than or equal to 1/4, which is less than or equal to f of pi over 2, or 0 is greater than, or excuse me, less than or equal to 1/4, which is less than or equal to 1. So given these, I'm going to say ideas, this proves, I'm going to actually change the, I'm going to say guarantees. That there is one value such that f of x equals d, and I'm going to say by the intermediate value theorem, so by the IVT. So let's think about what we have in this statement and why it's important that these certain things are there. To use the IVT, it needed to be continuous, and to use the IVT, those y values also had to match up. That d value, that 1/4, had to land in this range from 0 to 1, because that's where our function lives. It has to land in there first. If the value is outside of the range, the IVT can't say anything about it, essentially. So you have to say these two things. So given these two things, this guarantees that there's at least one value such that f of x equals d by the intermediate value theorem. Okay, that is it for Unit 1, I should say. Unit 1 is all about limits. Unit 1, we should all have some slight experience with, whether you were with me last year in calc, or you took calc or pre-calc or calc in the past, or, you know, we did some limits in pre-calc as well. So, we will work with limits in the first week, and after the first week, we will kind of branch off and do derivatives. So we're probably going to get out of limits pretty quick. If you guys have any questions, let me know. Have a good day.